But the first talk today is going to be learning to speed up query planning in graph databases. And we're going to have Doppa give the talk.
All right, thanks, Alan. So this talk is about speed up learning for graph databases. And this is a work done by Mohammad and Rezaur. We are all from Washington State University. And this work is funded by a Google Faculty Research Award. So because we are talking about speed up learning for databases, I thought I would give you a big picture about this two-way street between AI and databases. So there has been a lot of recent work in the sense of how to use database technology to improve AI algorithms. So some examples are how to improve statistical inference using RDBMS technology. So this work has mostly come out of Chris Ray's group. And also there has been a couple of very recent papers where they tried to scale up lifted inference and learning using approximate counting by compiling the statistical models into graph representations. And there also has been some work on feature selection using materialization optimization. So the other direction is how can you use AI techniques to improve databases? There has been some progress in the last 10 years or so, but one of the take-home message I would give is there are a lot more opportunities and there are a lot of questions which haven't been even asked actually in this direction. So to give you some examples, so there has been work on adaptive query processing in the context of relational databases, and mostly this work has been led by Amol, Jack Ives, and so on and so forth. And I was trying to read this literature for a while, and the only methodological advance I saw in this context was an RL formulation in the context of the EDIS project. So because Amol was a Joy Hellerstein student back in 2000, and that's where he picked the adaptive query processing kind of stuff. And if you look at the AI people, there are three AI people who worked in the context of databases. So one is Rao. He worked on automated planning for information integration. And the other one is Lisa Getour. She worked with Amol, and Dan World with Alan Harvey. The other kind of work which has been also done is how to predict the performance of queries before execution and using those models to do workload management. So what was my personal motivation to work on this problem? So I have been interested in speed up learning for a while. Mostly my dissertation work has been on structured prediction. And I was looking for a domain, and I really needed two requirements. One was there was ample room for speed up, and the second thing was there was more potential to build a higher level product. And I felt graph databases was a good fit because it's a more active and fertile area, and I could do a lot of technical stuff here. So just to motivate, graph search basically is employed in a lot of graph analytics applications, starting from knowledge graph search to cyber network security to social network analysis. So let's start. I will give you some background on graph query processing before I talk about any of the planning stuff. So the background is like this. So you have a data graph, so vertices and edges, and they're all labeled, right? And you have a query graph, which is a pattern graph, again, labeled vertices and edges. And the problem is pattern matching. You're given a scoring function to score candidate matches and in the data graph, and you want to find the top k scoring matches according to the scoring function, right? So that's the problem. So here is a very simple example in the context of knowledge graph search. So here is a query, and that is one of the matches basically from the data graph. And if you want to understand the natural language version, essentially what you want to find, the user wanted to find the artist who worked with J-Lo in a band, basically, right? So there are two aspects to graph databases. So one is scalability, other one is usability, right? So whenever the user, when he issues a query, the user has to use basically a structured query language. So there also has been work on issuing natural language queries, and that's not what we address in this work. So what are the main challenges in graph query processing? So the first challenge is the scale of the data. So there are lots of nodes and lots of edges and it's hard to do basically query processing. The second issue is that most of the computational problems are intractable, and heuristics are routinely employed, and these heuristics are designed by basically database designers. And the third and most important thing is that a lot of real-world applications need real-time response requirements, right? For example, cyber network security, right? You have an attack pattern and you want to search the cyber network graph to find, whether there is an attack pattern that is available or not, and you need really real-time response. So the key to address most of these challenges is what I call query planning. And in this context, what I mean essentially by query planning is the sequence of computational steps you have to do to answer the query. So the main research question we ask is, can we automatically improve the speed of query processing by analyzing the queries drawn from a target distribution, right? So to study this question, of course, we have to pick a query processing approach, right? And I just didn't want it to, look into any of the approach. So I wanted a little bit more general approach. So what I went with is this threshold algorithm framework. It's an old work, but it's pretty general work. So a lot of recent graph query processing has been inspired by the threshold algorithm framework, even though it was developed in the context of relational databases. In fact, a state-of-the-art graph query processing approach is based on this threshold algorithm framework. So let me give you a quick overview of what threshold algorithm is to motivate why we would need learning techniques. So the first step the threshold algorithm does is it decomposes the query into subqueries. So in this case, you have a pattern query and you decompose it into a bunch of star queries. The second thing it does is, in a round-robin fashion, right, it fetches partial answers for these star queries, right, and then it joins as needed, right? And the third step, most important, is for early termination, it dynamically maintains a lower bound and upper bound of the score, and it terminates when the upper bound is less than lower bound. So here is a simple illustration of the query plan from the TA framework, right? So if you looked at the previous example, the query was broken into 2 star queries, right? And if you see the highlighted path, essentially it takes a round-robin kind of selection, right? So you go to the first query, ask for k fetches, and the second query, k fetches, again back to 1, and so on and so forth. So the main drawbacks of this basic approach is that they follow a fixed fetch and join strategy, and the other drawback is that the upper bound estimation is kind of conservative. So even though the algorithm should supposed to be terminate, it actually keeps doing the work until it becomes really confident. So, this was Fagin's original paper from 2003. It got a 2014 Gödel Prize. And one of the open problems they posed in the paper, it's a very beautiful paper if those of you who want to read, they posed an open problem, said, well, can you find, it would be very interesting to find good heuristics to improve the speed of TA framework. And that's exactly what our work is doing. So the problem setup is like this. So you are given a training set of query answer pairs of the form Q, AP, right? So AP is the answer you get from the threshold algorithm framework from an unknown distribution. And what you want to learn is an adaptive policy to quickly guide the search to this answer, right? And the policy decisions at each search state consists of these 2 things, right? So there is a selection policy that you have to, it will pick for which subquery you want to fetch the partial answers. And the fetching policy says, well, you have picked this subquery. Now, how many partial answers you want to fetch, right? So those are the search decisions you have to make. So aside a quick overview, I don't have to probably tell this community what speed-up learning is, but still. So so those of you who don't know, Alan has an encyclopedia article on speed-up learning, and that's where I got started with speed-up learning when I was a grad student. So our problem essentially falls in this category. So we are looking at an inter-problem learning, which basically means that the policies should generalize to other query instances drawn from a query class, and the guarantees of correctness are mostly statistical because we use inductive learning. So to answer the main research question, we give an imitation learning methodology. So it consists of first defining a generic search space over the query plans. And the second step is to construct an automated expert to basically find target query plans which suit the learning objective. And the third step is to learn policies to imitate those target query plans. So coming back to the search space, each search operator in the search space has this form I comma delta, right? So I can take any of those T subqueries, or it can pick an halt action, right? So that's the action. And delta, we actually define a lower bound and upper bound, and we try to find some discrete values in this range, right? And the search stops if the policy picks a halt action. So the second step is this automated expert, right? So the green node is the terminal node, right? So this is a state where the answer is exactly the answer you get from the threshold algorithm framework, right? So you can see there are lots of these paths, and each path from initial state to this terminal state is a correct query plan. It will give you the same answer which the threshold algorithm would give you. So how do we define the target query plan? So any valid query plan which has the smallest computational cost in terms of execution from initial state to terminal state, that is what we want, because that will be very fast, right? So now the question is, how do you find them, right? So our approach is to use heuristic guided breadth first beam search, right? And we define kind of primitive heuristics. So these are functions, simple functions that take a state and a terminal state and gives you some kind of a real valued number, right? So some of the examples are how much the normalized time you took to reach this state, and the normalized score at this current state, and the cumulative difference between the partial answers, and so on. Now one thing we want to do is that, so we have these primitive heuristics, but we have to combine them, and we propose to combine them using weights, right? Now the question is, what would be these weights, right? So weights, good weights, the way we define is the weights that allow the beam search procedure to find high quality target query plans, right? So for example, here is the initial state, we are doing a beam search, right? And the terminal is found here, and the sequence of actions from the initial state to the terminal state corresponds to the target query plan. And the quality of the weights is essentially the computational cost of this target query plan we found. So now the question is, there are lots of weights, we have to find the right weights. So what we are after is the weights that will give you the highest average speed up over the training queries using this call. And this call is expensive, right? So you can use existing Bayesian optimization tools from off the shelf to find those weights. So the third part is policy learning. So here is a target query plan you get from the automated expert. You collect supervised learning examples at every state, one classification example for selection policy and one regression example for the fetching policy. Now, you aggregate all the classification and regression examples. So you give the classification example to a classifier learner and the regression examples to a regression learner, and you get your selection and the fetching policy. So let's quickly look at the experimental setup. So we have experimented with 3 knowledge graphs, and the query workload was generated using this benchmark framework, and we had 2,000 queries, and 50% of them were used for training, 20% for validation, and 30% for testing. So we used BaseOpt to find the weights, and we tried with different beam sizes, and B equals to 10 kind of saturated. We didn't get much improvement. So the baselines are the star framework, which is the TA algorithm, and we also plugged in random policies for the star to see how good it is. And we implemented, so there are 2 variants of our approach. One is with exact imitation, and other one is with Dagger, which is a more advanced imitation learning algorithm. So the evaluation metrics are speed up factor, right? So how much fast this particular algorithm is with respect to the baseline approach, and the accuracy, like how far you are in terms of the score. And the evaluation, the way we do is we compute an average over all the testing queries. So here are the two representative results from DBpedia and Freebase, right? So as you can see, the Oracle target query plan is computationally much more computationally efficient than the baseline approach, right? So now you can ask the question, can't we use the Oracle query plans by themselves? Why do we need learning, right? No, we can't use, because the primitive heuristics need access to the answer from the baseline algorithm. And the second point is that the breadth first beam search is kind of computationally expensive. So here are the numbers, right? So now an interesting thing is, so you can compare the exact imitation version, right? So we improve speed with small loss in accuracy, but still there is gap in terms of the performance with respect to Oracle, right? So we tried Dagger, right? And there is little to no improvement. And part of the reason is because of our objective, in a sense that we wanted to pick a policy that has the highest accuracy. So if you have to see speed on x-axis and accuracy on the y-axis, then you have these policies form a Pareto optimal kind of a curve, and we are picking the policy that has the highest accuracy, even though there are other policies that might have higher speed up. So this is the star approach, the basic approach with random policies. So it improves speed, but it loses accuracy significantly. Part of the reason is that it stops much earlier. So we also did a more fine-grained analysis to see, what are the analytical operations basically these query plans are doing. So as you can see, the star does a lot of fetch and join calls with small number of fetches. But if you look at Oracle query plan, it does basically a small number of fetch calls with large fetches, right? And if you look at star, the learned version of the query plan, it significantly improves over the star, but it is still far from the Oracle, right? So one of the issue here is that our policy representation needs to be improved. Right now it's hand designed. We also did some ablation analysis. So we have two policies, right? So selection policy and the fetching policy. So this is the configuration for the star, and this is the configuration for the learned version, right? And this is the version where you use the round robin policy for the selection and the learned fetching policy plugged in. So the same termination criteria as star, so you don't lose any accuracy, but you lose speed up. And the other one is just the flipped version of it. So we also did some transfer experiments, in a sense that we trained on different data sets and we tested on different data sets. And in general, the policy is generalized reasonably well. And the only anomalous thing was when we trained a policy on all the data sets together, it gave slightly better results on the Freebase, which we don't understand yet. So to summarize, what we talked about was speed up learning meets graph databases, and we tried to learn heuristics to speed up graph query processing, and we gave an imitation learning methodology and showed that we can achieve good speed up, somewhere between 5 to 50x depending on the size of the data graph. And we just scratched the surface. This was our first attempt at solving the problem. So the road ahead, we need to look at robustness, scalable learning, and representation learning for the policies. And the take-home message is that there are a lot of opportunities for AI to improve databases. And the second thing is that the learning methodology at a conceptual level is general, modulo the representation learning. That's all I have.
So now we have the second student get ready, and we have a couple of minutes for questions, if there are any. Any questions?
Go ahead.
It's very interesting application, but I was a little underwhelmed by the use of imitation learning, because in a planning community we like to think ahead, we like to think for the future effects of our actions and think sequentially. So do you believe that a reinforcement learning kind of a mechanism would not be a better fit for this kinds of problems?
Yeah, So the main challenges in formulating as reinforcement learning is designing the right reward function to basically trade off speed and accuracy. It's not very easy to do. So what you could do is that you could have speed as actually one reward function and accuracy as the other reward function, and you could trade off with some lambda, and you have to still vary across the lambda and learn and run basically a black box policy gradient kind of an approach to try out all the lambdas to find out the Pareto optimal policies and pick the best one. So instead, here we were just using the search to actually do that. It would be an interesting comparison to do this versus that experiment to see what is the computational cost of doing both and picking the best policy. Excellent question.